Let's talk about missing. You think you understand that word, right? If I say a ship has been lost forever, what do you picture? Destroyed, crushed, ceased to exist? Okay, so when NASA stops receiving signals from Voyager, what is actually happening? Does the spacecraft cease to exist? Or do we simply no longer hear it? This is what fascinates me. In physics, lost doesn't mean vanished. It just means you can no longer interact with it. And those are two entirely different things. In 1977, two metal objects were launched from Cape Canaveral, Voyager 1 and Voyager 2, thanks to a rare planetary alignment that allowed them to get slingshot boosts from the gravity of Jupiter and Saturn. They weren't designed to last forever. No one at NASA thought they'd still be operating 50 years later. Yet today, Voyager 1 is more than 160 astronomical units away from us, over 24 billion kilometers, and Voyager 2 is about 130 AU. If you send a radio signal from the Deep Space Network in California, it takes roughly 22 to 23 hours for it to reach Voyager 1. 23 hours just to say hello. Then another nearly 23 hours to get a reply back. That's not a human scale distance. That's a cosmic scale distance. But everything is gradually running down. The radioisotope thermoelectric generators, RTGs, using plutonium-238 are losing power by the watt each year. And when the signal goes silent, many people will say, that's it. No, it's not. According to the law of inertia, an object in motion stays in motion unless acted upon by a significant force. Out there's almost no drag. According to gravity, it remains bound within the gravitational field of the Milky Way. That means 5 billion years of silence ahead isn't a tragedy. It's the inevitable consequence of equations we understand very well. You might hear someone say that one day Voyager will leave the solar system. It sounds so definitive, so dramatic. But what exactly are we talking about? If you mean the heliosphere, that enormous bubble blown by the solar wind into space, then yes. When the spacecraft crosses that boundary, it enters the interstellar medium. But the heliosphere isn't a gravitational boundary. It's just the boundary of wind and plasma. The sun's gravity extends much farther. If we're serious about escaping the sun's influence, we have to talk about the Oort cloud, a vast spherical shell of icy bodies surrounding our entire stellar system. Its inner edge begins around 2,000 to 5,000 astronomical units. Its outer edge may stretch to nearly 100,000 UCAS, about 1.6 light years. That's the real scale of influence. Voyager is traveling at about 17 kilometers per second, equivalent to 38,000 miles per hour. Sounds fast, but put it in context. At that speed, it would take roughly 300 years to reach the inner part of the Oort cloud. 300 years, longer than the entire history of the United States. And to cross the whole structure, about 30,000 years. 3 times longer than the period since humans began building the first agricultural civilizations. So when you hear the phrase, leaving the solar system, pause for a second. Ask whether we're talking about the solar wind or about gravity. Because words can create a sense of finality, but gravity doesn't care about the names we give things. The sun keeps pulling, and Voyager, no matter how far away, is still responding to that pull. And once you realize Voyager hasn't truly escaped the sun's gravity in any absolute sense, a much more interesting question arises. What lies ahead for it? Not in a few years, not in a few centuries, but in tens of thousands and hundreds of thousands of years. Fast forward to 40,000 years from now. 40,000 years ago, modern humans were still painting in caves and hunting mammoths. 40,000 years from now, Voyager 1 will approach its closest encounter with a red dwarf star called Gliese 445 in the constellation Camelopardalis. The closest approach is estimated at about 1.6 light years. It sounds like it's going to meet that star. But let's clarify the number. 1 light year is about 9.46 trillion kilometers. Multiply by 1.6, and you're talking more than 15 trillion kilometers. On galactic scales, that's called close. On the scale of anything you've ever experienced on Earth, it's an almost infinite abyss. Voyager 1 won't enter orbit around Gliese 445. It won't be captured by that star's gravity. It will simply glide past the neighborhood, continuing its orbit around the galactic center like a metallic speck of dust in an ocean of stars. Voyager 2 has a similar itinerary. In about 40,000 years, it will come close to Ross 248 at roughly 1.7 light years. Ross 248 is another red dwarf, smaller and dimmer than our sun, but interestingly, it's moving in such a way that in about 33,000 years, it will briefly become the closest star to the sun, overtaking Proxima Centauri for a short cosmic moment. So Voyager 2 will glide past our closest star at that time. Not because it was aimed there, but because everything in the galaxy is moving, even the stars. That's something our intuition often overlooks. Stars don't sit still against an immobile backdrop. They drift, orbiting the galactic center at hundreds of kilometers per second. Push the clock even further, about 296,000 years, then Voyager 2 will approach the vicinity of Sirius, the brightest star in our night sky today. Sirius isn't just a bright point. It's a binary system consisting of Sirius A, a brilliant white-blue star, and Sirius B, a white dwarf, the dense remnant of a star once larger than the sun that exhausted its nuclear fuel. The closest approach between Voyager 2 and the Sirius system is estimated at about 4 light years, nearly 38 trillion kilometers. Once again, we use the word close generously. 4 light years is still a distance that light, the fastest thing in the universe, takes 4 years to cross. You start to see what's happening, don't you? Our scale is being stretched to the point where words lose their familiar meaning. In a galaxy roughly 100,000 light years across, where the average distance between stars is 4 to 5 light years, an object passing within a few light years of a star is considered an encounter. But it's not an encounter in the human sense. No collision, no flash of light when metal meets stellar plasma, no dramatic footage, no signal sent back to Earth saying, "We've arrived." By then, Voyager's transmitters will have been silent for ages. The RTGs won't have enough power to keep any systems running. The spacecraft will be cold, dark, and unaware of its own journey. There will be no audience standing out in that deep space to witness the moment it glides past Gliese 445, Ross 245, or Sirius. No astronomers waiting on the other side. Just motion, inertia, and gravity. The equations Newton and Einstein wrote, continuing to operate indifferently. And this is the real escalation. We're talking tens of thousands and hundreds of thousands of years just to pass by star systems at distances still measured in tens of trillions of kilometers. This isn't a journey to a specific destination. It's an orderly drift within a gigantic gravitational field. No destiny, no hidden purpose, just physics. And if you call distances like that close, then you begin to understand that in this galaxy, close is still unimaginably far. But what really makes me pause isn't the distance, it's the time. 40,000 years is just the beginning. 300,000 years is still a blink in the 225 million year cycle of the sun's orbit around the galactic center, while Voyager glides past those star systems. The continents on Earth will have shifted. Species will have appeared and vanished. The language you and I are using may no longer exist. And that tiny spacecraft weighing less than a ton will keep moving, not because it wants to, not because anyone is guiding it, but because it was given a velocity in 1977 and in deep space. Nothing is strong enough to take that velocity away. That's the strangest thing about these encounters. They aren't destinations, just incidental waypoints on an enormous gravitational curve. No applause, no audience. If you start imagining those encounters like in science fiction movies, dense fields of flying rocks, glowing asteroid belts, dramatic collisions, then I have to disappoint you in the best possible way. Space is so empty it's almost unbelievable. When we talk about the interstellar medium, the average density of matter there is about 1 atom per cubic centimeter. 1 atom. In a cube the size of your fingertip, compare that to the air you're breathing. At sea level, Earth's air contains about 10 mucal molecules per cubic centimeter. That's 10 billion molecules in the same volume. You might think you're living in a dilute environment, but compared to interstellar space, we're drowning in an almost unimaginably dense ocean. The difference isn't double, not a million times. It's billions of times. And that completely changes our intuition about what could happen to Voyager when the density is just 1 atom per cubic centimeter. The probability of an object a few meters across, like Voyager, colliding with anything large enough to cause serious damage over millions of years is extremely low. There are no meteor storms waiting out there. No thick streams of cosmic gravel like in Hollywood movies. Most of the path Voyager travels through is truly pure void, almost completely empty. Of course, space isn't perfectly empty. There is cosmic dust, charged particles, high-energy cosmic rays, but they are so sparse that over tens of thousands of years, Voyager might not hit anything more significant than a tiny speck of dust. And it's precisely that emptiness that allows the spacecraft to survive so long. On Earth, metal corrodes from oxygen and moisture. Steel rusts, aluminum oxidizes. Structures are gradually destroyed by wind, rain, and microbes. But in the deep vacuum between the stars, there is no oxygen, no water, no bacteria. Vacuum is an astonishingly good preservative environment. If you want to preserve a metal object for millions of years, put it in interstellar space where nothing can react with it. The main threat to Voyager isn't giant rocks hurtling toward it, but micrometeoroids, tiny dust grains, perhaps only a few microns across, but moving at tens of kilometers per second. When such a grain hits a metal surface, it can create a small pit. Not an explosion, just a scratch. But over hundreds of millions or billions of years, countless tiny scratches like that could gradually erode the surface, like extremely slow cosmic sandpaper. Still, that erosion rate is very slow. Estimates suggest the golden record attached to Voyager could still be readable after billions of years, precisely because the surrounding environment is too empty to destroy it quickly. The paradox is this: the most dangerous place for a metal object isn't deep space, but a planet with an atmosphere and weather like ours. Voyager drifts in such near-perfect vacuum that by the standards of chemistry and mechanics, it has almost nothing to fight against. No significant drag, no friction, no wind, just inertia. And that means for millions of years, even hundreds of millions of years, it will continue its journey without encountering any dramatic event. If you're waiting for a spectacular collision, you'll be disappointed. What's really happening is an almost perfect drift through an almost completely empty ocean. The near absolute emptiness of space might make you think Voyager is completely free, as if once it leaves the planetary neighborhood, nothing can hold it back. But this is where we have to be extremely careful with our intuition. Freedom from friction doesn't mean freedom from gravity. Voyager is moving at about 17 kilometers per second, equivalent to about 38,000 miles per hour. By human standards, that's a terrifying speed. A commercial airplane flies at about 900 kilometers per hour. Voyager is nearly 70 times faster. If you could drive a car at that speed, you'd circle Earth in under 3 hours. But the universe doesn't care about human intuition. It cares about energy and mass. Let's start with a familiar example: Earth's escape velocity. For an object to never fall back to this planet, it needs about 11.2 kilometers per second. If you throw a ball straight up, it falls back because you didn't reach that number. If somehow you could throw it faster than 11.2 kilometers slash, it would never return. That's escape velocity. Voyager easily exceeds that, and in fact had to reach much higher to escape the sun's pull at Earth's orbital distance. The escape velocity from the sun at our position is about 42 kilometers per second. Thanks to gravitational slingshots around Jupiter and Saturn, Voyager gained enough energy to never return on a closed orbit around the sun. But now scale it up to galactic level. The Milky Way isn't just a thin sparkling disk in the sky. It contains roughly 100 to 400 billion stars, billions of gas and dust clouds, plus a huge amount of dark matter we can't see directly but know exists from its gravitational effects. All that mass creates an enormous gravitational field holding the entire structure together, orbiting a center where Sagittarius A, a supermassive black hole about 4 million times the sun's mass, resides. To escape the combined pull of the entire galaxy from the sun's position, An object needs about 550 kilometers per second, equivalent to about 1.2 million miles per hour. Now put the two numbers side by side. Voyager's 17 kilometers slash and the 550 kilometers slash needed to leave the Milky Way. They don't just differ a little. They differ by more than 30 times, and energy scales with the square of velocity. That means the energy required to reach 550 kilometers slash is hundreds of times greater than the energy Voyager carries. If 17 kilometers dotties is like a very hard throw out of Earth, then 550 kilometers dotties is like throwing that ball with the energy of a supernova explosion. This isn't a small shortfall that can be made up with willpower or modest technology. It's a gigantic physical gap. Voyager is fast enough to escape the sun. It's not fast enough to escape the galaxy. And that's why it will never drift into the intergalactic void, where galaxy clusters are mere distant specks, millions of light years away. Instead, it will keep orbiting the galactic center along with the sun in an enormous orbit that takes roughly 225 to 250 million years per loop. In one such loop, Earth's continents will shift many times. Species will appear and go extinct. Perhaps humanity itself won't exist in its current form. But Voyager will still be bound in that gravitational dance. This isn't failure. This isn't tragedy. It's the inevitable consequence of mass and energy. You can't negotiate with gravitational equations. You can't tell the galaxy you have big ambitions. The numbers are the numbers. The mass of hundreds of billions of stars is the mass. And your velocity is either enough or it isn't. In this case, it isn't. And that reminds us of a truth I've always loved in physics. It's impartial, unsentimental, unpursuable. You can dream of flying out of the galaxy, but if you only have 17 kilometers per second in your pocket, you'll orbit along with it. If Voyager can't leave the Milky Way, then what will it do for the rest of its existence? It will orbit the galactic center, just as our sun has been doing for billions of years. Let's talk about what's called a galactic year, the time the sun takes to complete one orbit around the galactic center. The estimate is about 225 to 250 million years. 250 million years for one loop. To put it in perspective, dinosaurs appeared roughly 230 million years ago and disappeared about 66 million years ago. The entire dinosaur era, from appearance to extinction, happened in less than one galactic year. When the sun began that orbit, dinosaur ancestors didn't even exist yet. When it neared completion, dinosaurs were gone from the planet. Modern humans only appeared about 300,000 years ago. That means we haven't even covered 1,000th of a galactic year since we showed up. Even if you count from the Cambrian explosion around 540 million years ago when complex life burst forth. The sun has only completed about 2 galactic orbits for the entire known history of complex life. Our sun lies about 26,000 light years from the galactic center. There sits Sagittarius A, a supermassive black hole roughly 4 million times the sun's mass. You can't see it with the naked eye, but you know it's there from the way stars around it move at enormous speeds, bound by an undeniable gravitational field. The entire galaxy, 100 to 400 billion stars, plus gas, dust, and dark matter, orbits that center. Voyager, tiny and almost insignificant, is caught up in the same dynamical structure. It isn't shooting straight out like a bullet from a gun. Its orbit will be curved by the galaxy's total gravitational field, just like the sun's is. You can think of Voyager as an artificial comet, but instead of orbiting one star, it orbits the entire galaxy. One loop takes hundreds of millions of years. In that time frame, Earth won't resemble what it is today. Continents will merge into supercontinents, then split again. The Himalayas may erode into plains. Oceans may reshape and change levels many times. Millions of species will be born, evolve, then vanish. Mass extinctions aren't rare events in geological history. They're a natural part of evolution. In a single galactic year, many planet-scale events could occur. If you compress 250 million years into a calendar year, all of human history occupies just the last few hours of December 31st. From the perspective of galactic orbit, our civilization is a fleeting moment. but Voyager will keep orbiting. It doesn't care about biology, language, or the culture that created it. It only obeys inertia and gravity. What humbles me most isn't the length of a galactic year, but the fact that we're smart enough to calculate it. We know the sun's orbital speed around the center. We know the 26,000 light-year distance. We've measured the orbits of stars around Sagittarius A to infer the black hole's mass there. A creature that appeared a few 100,000 years ago on a small rocky planet has figured out the 250 million year cycle of a structure 100,000 light years wide. And the spacecraft we launched will keep participating in that cycle, completing orbital segments no living being has ever witnessed from start to finish. One galactic year is longer than the existence of dinosaurs, thousands of times longer than human history. In one such year, a civilization could rise and fall like a tiny spark. But the orbit continues, Voyager continues, no rush, no climax, just steady motion around the center of a galaxy whose mass is large enough to hold everything, including us, in the invisible embrace of gravity. If a galactic year already staggers you, then scale it down to just 1 billion years. It sounds more modest, but it's actually far more terrifying. 1 billion years from now for Earth isn't a gentle extension of the present. It's a complete restructuring. Start with plate tectonics. Continental plates move at a few centimeters per year, too slow to feel, but in 100 to 200 million years, a typical geological cycle. Oceans can open and close, continents can collide, then separate, supercontinents can form, then break apart. In 1 billion years, that process could repeat many times. Our familiar coastlines will be gone. The Atlantic may close. A new supercontinent may form, then be torn apart by fresh rifts. The Himalayas, the result of India colliding with Eurasia, may erode almost completely, not from sudden catastrophe, but from rain, wind, and time. Time is the slowest and most persistent erosive agent you can imagine. Our cities, even built with reinforced concrete and alloy steel, stand no chance against that scale. In a few tens of thousands of years, most unmaintained structures will collapse. In a few million years, erosion and tectonics will erase nearly every clear trace of civilization. In 1 billion years, no pyramids, no skyscrapers, no dams, no highways will remain. Even deep underground structures may be deformed by heat and pressure. Our record won't disappear in an explosion. It will be crushed, eroded, and recycled by geology. But the biggest change may not come from rock movement, but from atmospheric chemistry, silicate weathering, the process where atmospheric quark atom reacts with silicate rocks and gets locked into carbonate minerals, acts as a long-term thermostat for the planet. Over very long timescales, this process tends to draw down atmospheric CO and create a slab in hundreds of millions to 1 billion years. CO and PO could drop below the threshold needed for C3 and even C4 photosynthesis. That means complex plants will struggle, then disappear. Without plants, food chains collapse. Without food chains, complex animals can't survive. At the same time, our sun isn't standing still. It gradually brightens as it burns hydrogen in its core. In about 1 billion years, the sun's luminosity may increase by roughly 10%. It sounds small, but for Earth's energy balance, it's a huge change. Average surface temperatures will rise. The water cycle will intensify. Oceans will begin evaporating faster, and water vapor, a powerful greenhouse gas, will trap even more heat. A positive feedback loop may kick in. Models suggest that in about 1 billion years, Earth could enter a moist greenhouse state where most oceans gradually evaporate into the atmosphere, then get split by ultraviolet radiation, allowing hydrogen to escape to space. No asteroid impact needed, no sudden disaster, just time and the natural evolution of a middle-aged star. In that scenario, complex life, trees, animals, anything with a complex nervous system, will no longer exist. Heat-tolerant microbes might survive longer in harsh environments, but a blue-green planet with forests and oceans will be gone. And while Earth goes through all those changes, drifting continents, shifting atmosphere, evaporating oceans, disappearing complex life, Voyager will still be out there, orbiting the galaxy. no acid rain, no weathering, no erosion from wind and water. It doesn't need COHS. It doesn't need oceans. It doesn't care about carbon cycles or climate balance. While every trace of cities, nations, and civilization gets wiped from the surface of the planet that birthed it, that tiny spacecraft may keep following its orbit in the near-pristine void between the stars. That creates a strange contrast, a dynamic, living, constantly recycling and self-transforming planet with a race on material memory, the near-empty. Freezing void can preserve a piece of metal carrying our message for billions of years. 1 billion years is enough for Earth to become an entirely different world, but for galactic orbit it's just a small fraction of one loop. And Voyager, oblivious to biology or geology, will keep moving, carrying traces of a civilization that may have completely vanished from its own planet. The Sun is currently about 4.6 billion years old. It's in midlife, in the stable main sequence phase, where hydrogen in the core is fused into helium under such pressure that nuclear fusion releases enough energy to balance the gravity trying to collapse the entire star inward. It's a delicate equilibrium between outward radiation pressure and inward gravity. But no fuel burns forever. In about 5 billion years, most of the core hydrogen will be depleted. Then the core will no longer have enough thermal pressure to resist gravity and will begin to contract. As the core contracts, temperature skyrockets, igniting fusion in the shell around the core. The result is the Sun's outer layers swelling outward dramatically. The stable yellow star will become a red giant. In this phase, the Sun's radius may expand almost to 1 astronomical unit, roughly the current distance from Earth to the Sun. Picture that. The entire orbit Earth travels today could lie inside the glowing red envelope of a dying star. Mercury will almost certainly be swallowed. Venus will almost certainly have no chance of survival. For Earth, the details are still debated in models, but the general outcome isn't optimistic. As the Sun sheds its outer layers, it will lose mass, causing planetary orbits to shift outward a bit. But if the expanding envelope reaches Earth's orbit, frictional drag could spiral the planet inward, whether fully engulfed or merely scorched until the surface melts. Earth will no longer be a blue planet. The oceans will have evaporated hundreds of millions of years earlier. The surface may be molten, the atmosphere stripped away, and every material trace of life erased. After the red giant phase peaks, the Sun won't explode as a supernova. It lacks the mass for that. Instead, it will blow its outer layers into space, forming a glowing planetary nebula for a few tens of thousands of years, a brief cosmic moment. The remaining core will collapse into a white dwarf, an Earth-sized object carrying nearly the Sun's mass, extremely dense and initially very hot, then slowly cooling over the next billions of years. The solar system will become a white dwarf system with any surviving planets orbiting in faint darkness. And through all that violent transformation, Voyager won't be nearby. It will have left the planetary neighborhood billions of years before this scenario unfolds. When the Sun begins to swell, Voyager may be tens of thousands of astronomical units away, perhaps already beyond the Oort cloud, continuing its orbit around the galactic center. The Sun's expansion won't reach it. Radiation intensity falls with the square of distance. At Voyager's position, the difference will be only a minor change in the gravitational field as the Sun loses mass. It will adjust its orbit slightly, but it won't be swallowed, won't be incinerated. Stop and think about that contrast. The planet where life evolved, where there was biology, history, consciousness, and technology, may be wiped out or turned into a scorched rock. Meanwhile, a metal structure weighing less than a ton, assembled by finite humans in the 1970s, may continue existing in deep space, carrying a message from a world that has vanished. The Sun will go from stable yellow star to fiery red giant to cooling white dwarf, and Voyager will keep moving with no engine, no self-purpose, only inertia and gravity. While the central star of the system completes its main life cycle, that tiny spacecraft will still be part of the hundreds of millions of years per loop galactic orbit. When the Sun is just a cooling white core fading in the dark, Voyager may still be drifting among the stars, far from the ruins of the system where it was born. That isn't poetry. It's the unavoidable outcome of time, mass, and energy, quantities that never ask if we're ready. When you look at that entire panorama, Earth transformed, the sun becoming a red giant, then shrinking into a white dwarf, the planetary system restructured. A natural question arises. If Voyager can last that long, what exactly is it carrying? Not the scientific instruments, not the plasma detectors or magnetometers. Those will have shut down long ago when the RTG power runs out. What could survive for billions of years on the spacecraft is something far simpler: the golden record. A 12-inch gold-plated disc attached to the side of both Voyager 1 and Voyager 2. The idea for this object wasn't random. It was led by astronomer Carl Sagan, along with a small team of scientists and artists, including Anne Druyan and Frank Drake. Frank Drake wrote the famous Drake equation on the probability of extraterrestrial civilizations and was one of the pioneers of SETI. Anne Druyan, Sagan's close collaborator, played a central role in selecting content and designing the message. Their team had to answer an extremely interesting question. If you have only a small object that might last billions of years in space, and you want to send a message representing all of humanity, what do you put on it? The result was the golden record, a 12-inch copper disc electroplated with gold to resist corrosion and extend longevity in vacuum. It resembles an old vinyl record, but was designed to outlast any recording medium humans had ever created. Attached to it is a stylus, a diamond-tipped needle, mounted on the spacecraft. If another civilization ever finds Voyager and deciphers the symbols on the cover, they could place the stylus in the groove and play back the analog content etched inside. What's fascinating is how the team solved the language problem. They couldn't assume any other being in the galaxy would understand English, Chinese, or any human language. So they started with basic physics. On the cover is etched a diagram using the hydrogen hyperfine transition, the 21-centimeter wavelength of neutral hydrogen. This is one of the most common signals in astronomy, since hydrogen is the most abundant element in the universe. By using the cycle of this energy level transition as a basic unit of time and length, the designers hoped any scientific civilization could decode the measurement system used in the record. The cover also features a special map, the positions of 14 pulsars. Pulsars are rapidly spinning neutron stars that emit radio pulses with extreme precision. Each has a unique rotation period, like a cosmic fingerprint. By engraving the relative positions of 14 pulsars with respect to the Sun and specifying their periods, the golden record provides a celestial coordinate system that allows anyone who decodes it to locate the solar system at the time of launch. In other words, it's a cosmic map pointing to where this message originated. The disk sits inside a protective aluminum case mounted on the spacecraft, designed to minimize erosion from micrometeoroids and cosmic radiation. In the near vacuum of interstellar space, with no oxygen or water to cause chemical corrosion, this gold-plated disk could last an extraordinarily long time, potentially billions of years before cosmic dust grains erode the audio grooves beyond readability. But the most interesting thing about the golden record isn't the material or the engineering. It's the philosophy behind it. Its purpose isn't an invitation. It isn't a radio signal saying, "Come here." Carl Sagan and his collaborators knew very well that the odds of Voyager being found by another civilization in the vastness of space are extremely small. Interstellar space is so wide that two objects could drift past each other light years apart without ever noticing. The golden record wasn't designed as a realistic communication strategy. It's more like a statement, a message cast into the universe that an intelligent species once existed on a small planet around an average star. It says, "We were here, and if someday, millions or billions of years from now, another being finds it and understands the simple symbols etched on that gold surface, they will know that in a far corner of this galaxy, there was once a world with oceans, music, voices, and curiosity, great enough to send a message into the cosmic dark." If the golden record were just a metal disc attached to the side of Voyager, it would merely be an interesting technical detail. What makes it one of the strangest objects humans have ever created is the content we chose to put on it. And this is where you start to see the most fascinating thing about the project. It's not just science, it's also a decision about identity. Carl Sagan and his team understood very clearly that they couldn't cram all of human history onto a 12-inch disc. They couldn't recount every war, every invention, every civilization, every mistake, every beauty. They had to choose. And whenever you're forced to choose, you're not just describing an object, you're revealing what you think is most important. The golden record begins with greetings in 55 languages. Pause on that number for a moment. 55 languages aren't the full linguistic diversity of humanity, but they're enough to say one thing. We are not a single voice. There are ancient languages like Sumerian and Akkadian, modern ones like English, Spanish, Arabic, Hindi, Mandarin, Russian. There are formal greetings, casual ones. The messages aren't long. They don't try to explain quantum physics or recount the history of war and peace. They mostly just say the basics. Hello, peace be with you. We wish you well. That's remarkable. When given the chance to send a message into the cosmos, we didn't start with a political manifesto or a boast about technology. We started with courtesy. After the greetings comes music. And this is where the golden record becomes more of a spiritual portrait of humanity than a mere scientific document. The selection team included music from Bach, Beethoven, Chuck Berry, and many other traditions on Earth. Bach represents a kind of near mathematical order in sound. His fugues and partitas have a structure that even if you know nothing about European culture, you can still sense that here is an intelligence organizing sound according to sophisticated rules. Beethoven is different. His music has weight, drama, tension, and release. It feels like the human mind talking to itself through sound. Then you have Chuck Berry with Johnny B. Good, fast, lively, informal, not classical, but full of 20th century energy. Placing Bach, Beethoven, and Chuck Berry side by side was a bold move. It says that if you want to understand humanity, you can't just listen to what's refined and ancient. You also have to listen to what dances, electrifies, and reaches the masses. And that was an excellent choice, because civilization isn't built only with cathedrals and libraries. It's also built with concert halls, radio stations, live music clubs, and kids learning guitar. But the golden record doesn't just contain music. It contains the sounds of Earth itself, not as an abstract concept, but as a real place with wind, water, thunder, and heartbeats. There's thunder. That means they wanted to send the very atmosphere of this planet into space, send the feeling of electricity, of clouds, of a sky cracking with energy. There's the sound of ocean waves. Not a hydrodynamics equation, but the actual sound of water moving on a rocky planet with oceans. There's the sound of a human heartbeat. This one particularly fascinates me, because it's a simple but fundamental biological signal. If another civilization doesn't understand our speech or our music, perhaps they can still recognize that this is the rhythm of a living body. There are also birds, wind, whales, laughter, kissing, footsteps, machinery. In other words, they didn't just send human intelligence, they sent the environment that intelligence grew up in. Then come 115 images encoded in analog form. These images aren't printed on the disk, they're converted into electronic signals that can be reconstructed into pictures if decoded correctly. Their content ranges from science to everyday life. There's a diagram of the solar system. There's a picture of DNA structure as a way of saying this is the chemical grammar of life, where we come from. There are anatomical images of male and female bodies, a pregnant woman, children, hands, eyes, animals, insects, plants, mountain and ocean landscapes. There are people eating, learning, building, caring for one another. There are houses, bridges, engineering works. What matters isn't just what's included, but what's absent. No guns, no tanks, no bombs, no battlefields, no corpses, no symbols that human history has produced, just as much as art and music. That doesn't mean Sagan's team was naive enough to believe war doesn't exist. On the contrary, precisely because they knew war exists, the decision to exclude it is meaningful. They weren't trying to make a neutral report on humanity. They were making an ethical choice. If this is our one chance to tell the universe who we are, we want to be known for our capacity to create beauty, order, care, and curiosity, not for our capacity to kill each other. That's a selection. You could even call it an idealization. But I don't see it as a flaw. I see it as a fascinating thought experiment. When forced to summarize humanity in a small object, we didn't choose what's most statistically accurate. We chose what's best in aspiration. And that reveals a great deal. The golden record isn't a complete photograph of humanity. It doesn't contain everything. It isn't fair to the full chaos of history. But perhaps that isn't its job. Its job is to say that on a small planet around an average star, there once was a species that could listen to music, say hello, record thunder and waves, observe its own body, and believe that beauty deserves to be sent into the darkness, even when there's no guarantee anyone will be there to hear it. When you hear the story of the golden record, the first reaction is often, will anyone out there ever find it? That question feels natural, almost inevitable, because we're used to thinking in human terms. Sending a message means hoping someone receives it. But when you put that question into the real context of the galaxy, the answer becomes much colder. First, consider the distances between stars. In our local neighborhood in the Milky Way, the average distance between two stars is about 4 to 5 light years. 1 light year is about 9.46 trillion kilometers. So when we say nearby star, we're still talking tens of trillions of kilometers. The space between them isn't like a crowded neighborhood where objects constantly pass each other. It's like a vast desert where each grain of sand is thousands of kilometers apart. Now look at stellar density. In the Sun's neighborhood, the average density of stars is about 0.004 stars per cubic light year. In other words, if you draw a cube with each side 1 light year long, the chance of having a star inside that cube is only about 4 parts per thousand. This means most of the space in the galaxy is truly empty, even on the scale of star systems. Voyager isn't flying through a bustling city of stars. It's drifting through a near-empty region where distances between star systems are enormous. When you combine average distances of 4 or 5 light years with such low stellar density, you start to see the problem of finding Voyager. The spacecraft is only a few meters long, a metal object smaller than a truck. Imagine placing a truck in the middle of the Sahara Desert, then asking the odds that a random pedestrian walks exactly across that spot in a few thousand years. Now expand that desert to galactic scale about 100,000 light years across and stretch the time to billions of years. You begin to see how meaningless the numbers become. The reality is that the probability of Voyager colliding with anything larger than a dust grain in millions of years is extremely low. We already talked about that when discussing the density of interstellar matter, but the probability of it passing close enough to a planet with life or a technological civilization to be detected is probably millions of times smaller still. Remember that a civilization has to exist exactly when Voyager passes their neighborhood. They have to have technology to detect a small object in deep space. They have to be curious enough to retrieve it. And all of that has to happen while Voyager is passing through a time window that might be only a few thousand or tens of thousands of years compared to its hundreds of millions of years orbit. When you multiply all those tiny probabilities together, the result is effectively zero. This isn't pessimism, it's just mathematics. Space is too vast, the object too small, and the lifetimes of civilizations may be too short. So the golden record was never designed as a realistic strategy for communicating with extraterrestrial civilizations. It isn't SETI. SETI's search for extraterrestrial intelligence looks for radio or laser signals, because electromagnetic signals can travel thousands of light years. A metal disc attached to a small probe can't do that. It can only be read if someone physically touches it. Carl Sagan understood this perfectly. He didn't send the golden record because he thought there was a significant chance someone would hear Bach or Chuck Berry from it. He sent it for the symbolic meaning of the act itself. It's like throwing a bottle into the cosmic ocean with a note inside saying we once existed. Not because we're certain someone will find the bottle, but because writing the message and throwing it out has meaning in itself. It says that humanity isn't just a surviving creature on a small planet. We're a species that looks up at the sky and wonders if anyone else is out there. And when we had the chance to send a tiny trace of ourselves outward, we chose to send music, ocean waves, heartbeats, and greetings. So when you ask what the odds are of the golden record being discovered, the most honest answer is almost none. But that isn't a failure of the project. because its goal was never to maximize the probability of being found. Its goal was to do a very human thing. Leave a small trace in this vast universe. Just to say that for a brief moment around an ordinary star, there was a species curious enough to send its story into the darkness. If the probability of the golden record being found by another civilization is almost zero, then the far more interesting next question is, how long will it survive before the space environment itself destroys it? Because even though interstellar space is nearly empty, it isn't completely harmless. The greatest threat to Voyager on billion-year timescales isn't collision with asteroids or comets events that are almost impossible, but something far smaller, micrometeoroids. These are tiny cosmic dust grains, perhaps only a few microns to a few thousandths of a millimeter, drifting throughout interstellar space. Their size itself isn't frightening, but their velocity is. In the galactic environment, these dust particles can move at tens of kilometers per second. When such a tiny grain hits a metal surface at extreme speed, it acts like a miniature bullet. Each impact creates an extremely small pit on the material surface. Not an explosion, not a large hole, just a tiny scratch. But what matters here is time. When you're talking millions, hundreds of millions, or billions of years, billions of such tiny impacts start to add up. The metal surface can gradually erode the way sand wears down rock in a desert, except the process happens extremely slowly. Scientists have tried to estimate that erosion rate. Based on interstellar dust density and Voyager's relative velocity, models suggest the golden record could last from about 1 to 5 billion years before its audio grooves are worn down beyond readability. Pause on that number for a moment. 1 billion years is enough for Earth to completely change its climate and biology. 5 billion years is roughly the time for the sun to evolve into a red giant and end its main life cycle. That means this tiny, simple gold disk could last nearly as long as the very star that created our planetary system. What makes this seem paradoxical is that the best preservation environment for metal isn't in an Earth laboratory, but in the vacuum of space. On our planet, metal faces a very effective enemy, the atmosphere. Oxygen reacts with metal to form oxides, the process we call rusting. Water accelerates that chemical reaction. Temperature changes cause materials to expand and contract. Bacteria and soil chemicals continue breaking down surface structures. A car left outdoors for a few decades can corrode severely. A steel bridge needs constant maintenance to avoid destruction by the environment. But in interstellar space, there's no oxygen, no water, no microbes, no weather, no wind, no rain, no freeze-thaw cycles, no familiar chemical corrosion. Vacuum, in a sense, is a perfect preservative environment. That's why the Voyager designers gold-plated the copper disk of the golden record. Gold is an extremely chemically inert metal. It doesn't oxidize easily, and in a vacuum environment, it's even more stable. That gold layer wasn't to make the disk look luxurious. It was a protective coating against erosion and chemical reaction over extremely long time scales. When you compare this to the lifespan of objects on Earth, the difference is astonishing. A paper book might last a few hundred years if well preserved. A stone statue might last a few thousand years before eroding. But a gold-plated metal disc drifting in vacuum can retain its structure for billions of years. That means the golden record could outlast most material traces of the civilization that created it. Cities, monuments, libraries, computer hard drives, all of those depend on Earth's environment and will be destroyed by geology and climate over long periods. But that gold disk out there only faces an extremely slow process. Tiny dust grains hitting it in the darkness between the stars. So when we talk about Voyager's future, what may end the story isn't a dramatic catastrophe. No explosion, no gigantic collision, just a gradual, almost imperceptible abrasion process unfolding over billions of years until the tiny grooves etched on the gold surface finally become too faint to tell the story they once held. When you put all of that together, the slow erosion by micrometeoroids, the near-perfect vacuum environment, and the potential billion-year lifespan of the golden record, an interesting paradox begins to emerge. That small disk could outlast the very planet that created it. Earth is a dynamic, living world, constantly changing. Plate tectonics continually grind up and recycle the planet's crust. Mountains rise then erode. Oceans open then close. Over hundreds of millions of years, most of the planet's surface gets completely restructured. What we build, cities, monuments, dams, factories, exists for an extremely short time compared to that geological rhythm. A building might last a century. A pyramid might last a few thousand years. But millions of years are enough to erase nearly every architectural trace from the planet's surface. Over hundreds of millions of years, even rocks-bearing fossils can be melted, crushed, or recycled into new crust. So there's a very real possibility that the golden record, a small metal object drifting in space, could survive longer than most material traces of the civilization that made it. That leads to a profound paradox. Information can outlast the environment that gave it birth. A species evolves on a rocky planet around an ordinary star. They develop language, music, science. They etch part of their story onto a gold disk and launch it out of their star system. Billions of years later, the planet where they once lived may have changed completely, or even ceased to exist, but the information they left behind continues drifting among the stars. This sounds almost philosophical, but it ties directly to physics. We often talk about entropy, the tendency of physical systems to move toward greater disorder over time. The second law of thermodynamics says that in an isolated system, total entropy will increase. That's usually understood intuitively. Everything eventually breaks down. Order turns to chaos. But what matters is that entropy describes the overall trend, not the fate of every individual structure. A structure can persist for a very long time if its surroundings lack many mechanisms to destroy it. In Earth's atmosphere, there are countless such mechanisms: chemical reactions, erosion, biology, temperature swings. But in the cold, still vacuum between the stars, many familiar destructive processes disappear. Entropy still increases on cosmic scales, but the rate at which a simple metal object is destroyed can be extremely slow. That allows small structures like the grooves on the golden record to last far longer than our intuition about decay suggests. In other words, order can endure in the right environment. A few micrometeoroids every million years aren't enough to instantly destroy a metal surface. The process can take billions of years, and during that time, the information etched on the gold surface persists. But there's another aspect to this paradox. Matter doesn't care about memory. The atoms that make up the golden record don't know they're carrying Bach's music or Earth's ocean waves. They're just copper and gold, arranged in a specific geometric pattern. If the grooves wear away, the atoms still exist. If the disk breaks, the metal fragments still exist. Physics doesn't distinguish between a meaningful object and a meaningless one. Meaning is something assigned by conscious beings with memory and culture. In the material universe, there is no concept of memory. There is structure, energy, motion. So the golden record represents something very special. A material structure designed to carry information about a conscious species in a universe where matter itself knows nothing about the meaning of that structure. If no one ever reads it, it's just a metal disk quietly orbiting the galaxy. But if someone decodes it, those tiny grooves on the gold surface become the voice of a planet that may have vanished long ago. When you think long enough about that paradox, a message that might outlast the very world that created it, you start to realize something far deeper about the universe. Physics doesn't care at all. There's no pre-written cosmic purpose hidden somewhere in the equations. No grand plan concealed in the structure of the galaxy. The laws governing Voyager's motion have no knowledge that it carries music, greetings, or images of humans. They only know mass, distance, and velocity. When Newton wrote the equations describing gravity, he didn't need to include concepts of hope, memory, or civilization. That leads to a profound paradox. Information can outlast the environment that gave it birth. A species evolves on a rocky planet around an ordinary star. They develop language, music, science. They etch part of their story onto a gold disk and launch it out of their star system. Billions of years later, the planet where they once lived may have changed completely, or even ceased to exist, but the information they left behind continues drifting among the stars. This sounds almost philosophical, but it ties directly to physics. We often talk about entropy, the tendency of physical systems to move toward greater disorder over time. The second law of thermodynamics says that in an isolated system, total entropy will increase. That's usually understood intuitively. Everything eventually breaks down. Order turns to chaos. But what matters is that entropy describes the overall trend, not the fate of every individual structure. A structure can persist for a very long time if its surroundings lack many mechanisms to destroy it. In Earth's atmosphere, there are countless such mechanisms: chemical reactions, erosion, biology, temperature swings. But in the cold, still vacuum between the stars, many familiar destructive processes disappear. Entropy still increases on cosmic scales, but the rate at which a simple metal object is destroyed can be extremely slow. That allows small structures like the grooves on the golden record to last far longer than our intuition about decay suggests. In other words, order can endure in the right environment. A few micrometeoroids every million years aren't enough to instantly destroy a metal surface. The process can take billions of years, and during that time, the information etched on the gold surface persists. But there's another aspect to this paradox. Matter doesn't care about memory. The atoms that make up the golden record don't know they're carrying Bach's music or Earth's ocean waves. They're just copper and gold, arranged in a specific geometric pattern. If the grooves wear away, the atoms still exist. If the disk breaks, the metal fragments still exist. Physics doesn't distinguish between a meaningful object and a meaningless one. Meaning is something assigned by conscious beings with memory and culture. In the material universe, there is no concept of memory. There is structure, energy, motion. So the golden record represents something very special, a material structure designed to carry information about a conscious species in a universe where matter itself knows nothing about the meaning of that structure. If no one ever reads it, it's just a metal disk quietly orbiting the galaxy. But if someone decodes it, those tiny grooves on the gold surface become the voice of a planet that may have vanished long ago. When you think long enough about that paradox, a message that might outlast the very world that created it, you start to realize something far deeper about the universe. Physics doesn't care at all. There's no pre-written cosmic purpose hidden somewhere in the equations. No grand plan concealed in the structure of the galaxy. The laws governing Voyager's motion have no knowledge that it carries music, greetings, or images of humans. They only know mass, distance, and velocity. When Newton wrote the equations describing gravity, he didn't need to include concepts of hope, memory, or civilization. The solar system appears around early September. Simple life on Earth begins not long after. But modern humans only appear in the final minutes of December 34. All of recorded human history, from the first cities in Mesopotamia to spacecraft, is even smaller. It occupies just the last few seconds before the cosmic year ends. Even if you scale it down to human history alone, that brevity is still astonishing. Homo sapiens has existed for about 300,000 years, but most of that time we lived in small hunter-gatherer groups, with no cities, no writing, no modern science. Agriculture appeared only about 10,000 to 12,000 years ago. The first civilizations with writing and states are only about 5,000 years old. All of modern science, from Galileo, Newton to Einstein, occupies just the last few hundred years. And if you want an even closer example, look at a specific country. The United States, one of the youngest but most influential nations in the modern era, has existed for only about 250 years. 250 years compared to Homo sapiens through 100,000 is already tiny. But compared to the universe's 13.8 billion years, it's practically zero. Using the same cosmic year comparison, the entire history of the United States would unfold in a tiny fraction of a second right before midnight. This doesn't mean human history isn't important. It just means the scale of the universe is vastly larger than the scale we're used to thinking in. Stars were born and died billions of years before our distant ancestors walked on two legs. Galaxies collided and merged long before Earth formed. And even after humanity disappears, whether in thousands or millions of years, the universe will continue evolving for billions more. Voyager is a small but powerful example of this disparity. It was launched in 1977, an extremely brief moment in human history. but its orbit around the galaxy could last hundreds of millions of years. The golden record attached to it could survive billions of years before complete erosion. That means an object built by a civilization only a few 100,000 years old can last many times longer than the entire history of that civilization. This doesn't make humans meaningless. On the contrary, it makes our story more astonishing. In a universe nearly 14 billion years old, on a planet formed 4.5 billion years ago, a recently emerged species developed intelligence enough to measure the age of the universe, calculate galactic orbits, and send a small spacecraft out of its star system. We are tiny in time and space, but we have the ability to understand things larger than ourselves. And perhaps that's the most remarkable thing. A creature existing for a few 100,000 years can look at a 13.8 billion-year-old universe and begin to understand how it works. But right at the point where you feel smallest before the scale of the universe, something else begins to emerge. And it's almost a beautiful paradox. Because although we are tiny to the point of near meaninglessness in time and space, we have the capacity to comprehend things vastly larger than ourselves. Think about the tool that allows us to do that, the human brain. The average adult human brain weighs about 1.3 kilograms, a soft mass of tissue consuming about 20 watts of power less than a desk lamp. It's made of roughly 86 billion neurons, each connected to thousands of others. Physically, it's just a complex network of chemistry and electrobiology shaped by biological evolution on a small rocky planet. But that tiny structure can do something astonishing. It can understand the universe. That 1.3 kilogram is what enabled us to calculate planetary orbits, measure distances to stars, and even describe the motion of the entire galaxy. Think about that seriously. A creature evolved to hunt on African savannas can now calculate that the sun is about 26,000 light years from the galactic center and takes roughly 225 to 250 million years to complete one orbit. None of our natural senses can directly perceive such distances or timescales. We can't see a galactic orbit. We can't live long enough to witness it. But through mathematics and observation, the human brain can infer it from data. The same is true for the sun's future. None of us will live to see this star become a red giant, but we understand the process because we understand nuclear physics and stellar structure. By observing millions of other stars at different stages of stellar life, astronomers can reconstruct the evolutionary story of a sun-like star. We know that when core hydrogen is depleted, the core contracts, outer layers expand, and the star becomes a red giant. Not because we've witnessed the whole process on the sun, but because we understand the equations governing it. The real wonder here isn't in the stars themselves. Stars just obey physics. The wonder is that a biological creature can discover those equations. Mathematics is the tool that lets us transcend the limits of our senses. When Newton wrote the equations of motion and gravity, he created a language that could describe both a falling apple and planets orbiting the sun. When Einstein expanded those ideas with relativity, he gave us a deeper understanding of space and time. And by applying these mathematical tools, we can predict the future of a spacecraft in hundreds of thousands of years, or the future of a star in billions of years. Pause and look at this paradox. A 1.3 kilogram brain, evolved through natural selection to solve very practical survival problems, has the ability to write equations describing an entire galaxy. That's not obvious at all. No law of physics requires that creatures evolving on a planet must be able to understand the universe, but somehow evolution produced a nervous system capable of doing so. That mathematical capacity is the most extraordinary thing in the story. Voyager, the Golden Record, telescopes, and spacecraft all are consequences of something more fundamental: humanity's ability to discover the abstract laws of nature. We don't just live in the universe, we understand it, at least in part. And when a tiny creature on a small planet can look up at the sky, write an equation, and from it predict what will happen to a spacecraft in billions of years, that may be the real miracle in this entire story. When you understand all of that, understand galactic orbits, understand the life cycles of stars, understand that a small gold disk could last billions of years, you begin to see the strangest part of the Voyager story. Most of its journey will take place in complete silence. In the first few decades after launch, Voyager was still talking to us. Its radio signals so weak that by the time they reached Earth, they were like a teaspoon of energy spread across the area of an entire city. Were still picked up by the giant antennas of the Deep Space Network. Those signals brought back data about magnetic fields, plasma, cosmic rays, and the environment beyond the heliosphere. But that only lasts for a finite time. Voyager's power comes from radioisotope thermoelectric generators, RTGs, using plutonium-238. That isotope decays slowly and produces heat, and that heat is converted into electricity. But radioactive decay means power gradually decreases over time. Each year, Voyager loses a small fraction of its electrical power. At some point, there won't be enough electricity left to operate the radio transmitter. When that happens, Voyager will send no more signals. No goodbye, no final message, just silence. From Earth's perspective, that will be the moment we lose contact with one of the farthest objects ever created by humanity. But from the perspective of physics, nothing special happens. The spacecraft doesn't stop. It doesn't disappear. It simply continues moving along its trajectory as it always has. After the radio signal goes quiet, there will be no way to know exactly where Voyager is every minute. No real-time data. No radio pings traveling billions of kilometers. For most of its future millions, hundreds of millions, even billions of years, Voyager will drift in what we could call 5 billion years of silence. No signals, no radio, no data coming back, no one standing there listening, no mission control, no scientists waiting for the next data packet. The spacecraft won't know it's silent because it has no consciousness. It doesn't know it's carrying a message. It's just a metal structure obeying inertia and gravity, and throughout that unimaginably long period, the orbit continues. It keeps circling the galactic center along with hundreds of billions of other stars. It keeps passing through regions where new stars form, where old stars die, where gas clouds collapse and explode into new planetary systems. But no one on Earth hears anything during that journey. Perhaps when Voyager glides past some star in tens of thousands of years, humanity will have vanished. Perhaps another civilization will have arisen on Earth, but won't know or care about the ancient spacecraft drifting in the galaxy. Or perhaps humanity will still exist, but Voyager will have become a minor footnote in science history books, like the first sailing ships that crossed the oceans. The only certainty is that the motion doesn't stop. The orbit doesn't need an observer. Newton's and Einstein's equations don't need radio signals to remain true. So while from a human perspective, Voyager's journey seems to end when the last signal fades, from the universe's perspective, the real journey is only just beginning. And most of that journey, almost all of it, will unfold in a silence lasting roughly 5 billion years. If you want to picture what Voyager will become in the very distant future, there's a pretty interesting comparison. Think of it as a comet, but an artificial comet. When we talk about comets, you usually imagine a chunk of ice and rock flying across the sky with a long, bright tail. But most of the time, comets have no tail at all. They're just small, cold, dark chunks of matter drifting quietly in deep space. Only when they pass close to a star does ice start to vaporize and create the glowing tail we see from Earth. Outside those moments, they're just wandering objects, drifting from one star system to another, sometimes for millions of years without anyone noticing. Voyager in the future will be very much like that. After its instruments shut down and the radio signal stops, the spacecraft will no longer be a scientific laboratory. It will just be a small piece of metal moving by inertia in the galaxy's gravitational field. No active engines, no orbit adjustments, no guidance systems. Just pure motion according to the laws of Newton and Einstein. Dynamically, it will behave like a comet or an asteroid ejected from its original star system. But there's one important difference. Natural comets are made of ice, rock, and dust remnants of the planet formation process. Voyager is different. It's made of aluminum, titanium, copper, electronics, and a gold disk attached to its body. Instead of being a product of condensation in a protoplanetary disk, it's a product of engineering. That makes Voyager a completely different kind of object, an artificial object drifting in interstellar space. When astronomers study the galaxy, they know that many small objects can be ejected from their star systems due to gravitational interactions. When a giant planet like Jupiter perturbs the orbits of asteroids or comets, some can be accelerated enough to escape the system. Those objects become interstellar wanderers, drifting through the galaxy like nature's unmanned ships. Voyager went through a similar process, except it was engineered. As it flew past Jupiter and Saturn, the gravity of those giant planets bent its trajectory and sped it up, a technique engineers call gravity assist. The effect was like a gigantic gravitational slingshot. A tiny fraction of the planet's orbital energy was transferred to the spacecraft, allowing it to accelerate and travel farther. The result is that Voyager gained enough velocity to leave the planetary region of the solar system and enter interstellar space. From the galaxy's perspective, this makes Voyager very much like a comet ejected from its original system. It will drift in the Milky Way's overall gravitational field, orbiting the galactic center just like hundreds of billions of other stars. During that journey, it will sometimes pass near other star systems, not because it's aimed at them, but because in a galaxy with hundreds of billions of stars, orbits occasionally bring objects close together. Close, in galactic terms, is still very large, usually a few light years. But astronomically, that still counts as an encounter. In those moments, Voyager will be exactly like a tiny comet flying through the outer edges of another star system. No one on board to observe, no cameras operating to take pictures, no signals sent out. Just a small object gliding past the light of an unfamiliar star and continuing its journey into the darkness. What makes this image special is the origin of that object. Most objects wandering between the stars are products of natural processes. Voyager is not. It's the result of curiosity from a species living on a small planet around an average star. That means that in the entire history of the Milky Way, this may be one of the first artificial objects ever sent out of its star system to drift among the stars. Not an active probe, but a technical relic, a fragment of a civilization, joining the natural flow of wandering objects in the galaxy. In that sense, Voyager will become something very much like a comet, but with a historical difference. Instead of being a remnant of planet formation, it's a remnant of intelligence. And over millions of years to come, it will drift through the galaxy like a small metal comet, carrying traces of a world very far behind. Looking at that journey, there's a very clear lesson physics always reminds us of. Physics always wins, not in a pessimistic sense, but in the very simple sense that natural laws ultimately always determine what happens. Voyager may be a tremendous human technical achievement, but it remains completely bound by the same rules that govern every other object in the universe. It cannot leave the Milky Way. To escape the galaxy's gravitational field from the sun's position, an object needs about 550 kilometers per second more than 2 million kilometers per hour. Voyager is moving at about 17 kilometers per second. That's an astonishing speed by human engineering standards, but by galactic standards, it's just a leisurely drift. That means no matter how long it travels, it remains bound within the gigantic gravitational field created by hundreds of billions of stars that make up the Milky Way. It will orbit the galactic center just like the Sun and other star systems, only on a slightly different trajectory. It also isn't immortal. Some people like to imagine that Voyager will last forever, but physics doesn't allow that. Over very long timescales, every material structure is subject to entropy. Micrometeoroids will keep hitting the spacecraft for millions, hundreds of millions of years. Cosmic radiation will break down molecular structures. Tiny thermal vibrations will gradually alter materials. The process is very slow in interstellar vacuum, but it never stops. After billions of years, metal surfaces will erode, joints will weaken, mechanical structures may fracture into smaller pieces. Voyager won't keep its perfect spacecraft shape forever. It also isn't immune to rare but possible events. Over hundreds of millions of years, there's a chance, though small, that it could be hit by another small celestial body, or its orbit could be altered by a close gravitational encounter with some star. In the galaxy, such events are very rare. But when you talk about billions of years, rare no longer means never. Still, what's interesting is that even though it isn't immortal and isn't immune to entropy, Voyager also doesn't vanish easily. Interstellar space is an extremely quiet environment. No wind, no water, no oxygen to cause corrosion. The destructive processes familiar on Earth are almost non-existent there. So while a car on Earth can rust away and disappear in a few centuries, a metal structure in space can last millions or billions of years before complete destruction. This creates a strange state. Voyager isn't immortal, but its lifespan can far exceed that of many structures on the planet that created it. During that time, it continues to exist as a physical object in the galaxy. It isn't active, doesn't think, doesn't send signals, but it still has mass, still has inertia, still feels the pull of gravity. In a purely physical sense, it remains part of the moving universe. And that's where the lesson, physics always wins, gets interesting. We can build complex machines, send them out from our planet, even put our messages on them. But ultimately, their fate is still decided by simple laws that existed long before humanity appeared. Inertia keeps them moving. Gravity bends their paths. Entropy slowly breaks down their structures. Those laws don't care that Voyager is an engineering achievement or a symbol of human curiosity. They just keep operating. And so Voyager won't leave the Milky Way. It won't last forever, and it won't escape entropy. But during the very long time before those processes finish, it also won't disappear. It will keep drifting, orbiting the galaxy along with the stars, like a small piece of human history carried along in the vast flow of the universe. Looking at the entire Voyager story from that perspective, galactic orbit, entropy, billions of years, a natural question arises. What exactly did we send out there? Because on the surface, Voyager is just a small scientific machine, a metal mass of about 700 kilograms or so, carrying a few measuring instruments, an antenna, and a gold disc. But if you look a little deeper, you realize that what we sent isn't really a spacecraft. What we sent is an idea. Throughout human history, many great actions of civilizations have been driven by ambition, ambition to expand territory, control resources, conquer new lands. When ships crossed oceans in past centuries, they often carried soldiers, national flags, and plans for colonization. But Voyager isn't like that. It carries no army. It carries no plan to colonize stars. It carries no tools to seize another planet. Instead, it carries the sound of ocean waves, falling rain, a human heartbeat, and music from many different cultures. That says something very interesting about the nature of this mission. This isn't a strategy. It isn't a plan for expanding power. Voyager isn't the first step in galactic conquest. It's an act of awareness. A small creature on a rocky planet looked up at the sky and asked, if someday someone out there finds this, what will they know about us? And our answer wasn't weapons, wasn't military technology, wasn't diagrams of defense systems. Instead, we sent very different things. Greetings in 55 languages, music from many cultures, images of people, families, everyday life. That means the golden record isn't a strategic message. It isn't part of SETI in the sense of systematic contact search. The odds of another civilization finding Voyager are extremely small. The distances between stars are too vast, and Voyager is too tiny. The designers of the golden record understood that perfectly. So its purpose wasn't to ensure someone would receive the message. Its purpose was to say one simple thing. We were here. That statement, we were here, sounds simple, but it carries profound meaning. It's a declaration of existence. A conscious species appeared on a planet orbiting an ordinary star in an ordinary galaxy. And that species developed enough curiosity to observe the universe, understand part of its laws, and send a small message into the space between the stars. What matters here isn't whether the message gets read. What matters is the act of sending it. Because that act says so much about the nature of intelligence. When a self-aware species starts asking questions about its place in the universe, one natural response is to want to leave a trace, not to conquer the universe, but to say that we once existed in it. Voyager thus becomes a kind of cultural fossil launched into space. On Earth, fossils tell us which creatures once lived here millions of years ago. The golden record does the same, but on galactic scale. If someday in millions or hundreds of millions of years another intelligence finds it, they won't just find a piece of metal. They'll find evidence that a civilization once existed around a star very far away. And perhaps that's the most interesting thing about Voyager. We didn't send ambition. We didn't send power. We sent curiosity. A creature looked at the sky and wanted to know what was out there. And when you look at that story from afar, from the distance of billions of years and hundreds of billions of stars, what Voyager really carries isn't a spacecraft. It carries a question. And when you look back at the entire story from the beginning, from when the spacecraft left Earth, flew past the giant planets, crossed beyond the heliosphere, and kept drifting into interstellar space, three simple ideas start to stand out very clearly. The first idea is that Voyager doesn't really die. We often use very human words to describe machines. It works, it breaks, it ends. But in physics, those concepts aren't entirely accurate. When the last radio signal fades, Voyager doesn't vanish. It doesn't cease to exist. The only thing that ends is its ability to communicate with us. The scientific instruments will go quiet. The radio transmitters will stop broadcasting, and the deep space network will receive no more faint signals from the deep void. But the spacecraft itself keeps moving. Inertia keeps it hurtling through the galaxy. Gravity keeps bending its path little by little over millions of years. From Earth's perspective, Voyager will become a missing object. But from the universe's perspective, it's simply an object continuing its journey. The second idea is that we are bound by gravity, and that isn't a sad limitation, but a profound physical fact. Voyager is fast enough to leave the planetary region of the solar system, but not fast enough to leave the Milky Way. The galaxy's gravitational field, created by hundreds of billions of stars and a huge amount of dark matter, holds everything in a slow dance around the galactic center. The Sun orbits Sagittarius, A, on a cycle of about 230 million years, and Voyager will do the same. That means no matter how long the spacecraft drifts, it remains part of this galaxy. It will pass through spiral arms, glide past gas clouds where new stars form, and keep orbiting the galactic center along with all the other star systems. The universe isn't an undefined void where everything flies off infinitely. It's a structure held together by gravity, where large and small objects all participate in the same shared motion. The third idea, and perhaps the most important, is that what we really left behind isn't the spacecraft, but the curiosity that created it. Voyager exists because a species developed the ability to ask questions. Simple questions at first. What are those bright dots in the sky? How do the planets move? How does gravity work? From those questions, we developed mathematics, physics, engineering, and ultimately the ability to send a machine out of our star system. The Voyager spacecraft is therefore not just a technical object. It's a consequence of curiosity. And that curiosity may be the most important legacy humanity carries into the universe. The golden record may last billions of years, but even if it's completely eroded by micrometeoroids, something more important remains. The fact that a civilization curious enough to send it once existed. In a vast and mostly silent universe, the act of asking questions may be the most special thing intelligence can do. And that leads to one final thought I really like. When Voyager's signal goes silent, many people will say the spacecraft has fallen into silence. But silence doesn't necessarily mean emptiness. In physics, silence often just means absence of signal. No radio waves, no data, no sound. But in Voyager's case, that silence still carries a story. It carries the orbit of an object continuing to move through the galaxy. It carries a gold disk with music and images from a distant planet. And above all, it carries proof that somewhere in the Milky Way there once existed a species curious enough to ask big questions about the universe. As long as those questions exist, the silence of space will never be completely empty, because in that void there are still traces of curiosity. And Voyager is one of the smallest but most enduring traces. If you find this story makes you look at the universe in a different way, please hit subscribe and join me on the next journeys exploring physics and the strangest ideas of the universe. For now, thank you for listening, and I'll see you in the next question we ask the universe together.